Testing. So let's get started. I guess let us briefly review the what we covered last class, and then we continue. So the plan is to try to finish most of it. If we can't finish, and your first homework will be released, I think, tomorrow, because I've the other section haven't finished topic 1, almost done, but still a little bit left there. So I will be expecting you for the first homework will be you'll be submitting that by, I think, the end of next week. Okay. So given 10 days or more to do it. Okay. So let us start. Okay. Before we start, let me know if you have any questions on the material cover. If no, then let's get started. So because after the weekend, probably it's not easy to remember everything. So let us briefly review what we have done. So we are going to define probability, right? And we do it in terms of axiomatic definition. So it's kind of disconnecting, somewhat disconnecting what we observe in the real world, because classically the idea of probability is defined at what we define as a long run frequency, right? It's just like you have a random experiment, which suppose you can repeat many times, and it would be defined the ratio, right? And sometimes you can define this, right? Because something can be repeated, right? But sometimes you really can't repeat. So the idea of having a random experiment potentially can repeat many times is not possible, right? You can imagine, you can control things, then you can repeat, right? Just like recently you have an earthquake in Taiwan, and potentially can't repeat this process because it's like coming from the underground reaction and action of the earth core, which potentially can't really repeat itself. So but that being said, I mean, this classical idea of ratio of a long run many times experiment is still a well-defined, and it is the way we start our idea of probability, right? But it would not be applicable for many situations, right? So that's why we need to define probability that would be unrelated to the real world, okay? But of course, later when we learn topic 5 or 6, when we talk about law of large number, central limit theorem, those ideas actually we will convert back to this idea of what we actually keep doing things, do sampling things, actually would end up in getting what is likely to be true in the underlying population. But that would be something we will discuss a little bit later. But the way we proceed is, okay, we define what is random experiment, right? It's like something we can repeat. Outcome is the possibility of an experiment, right? An event is a group of outcomes, right? And sample space is the event that contains all possible outcomes, right? Then later we define what is intersections, right? What a union, what a complement, right? Intersection means you include only the common elements, okay, common outcomes. And union contains all possible outcomes, right? And complement is the things that in the event, not in the event, but in the sample space, right? So basically just like go to the sample space, take out whatever in A, then A complement. And we learned 3 different ideas that we learned was mutually exclusive, right? It's like they can't happen at the same time. We also learn what exhaustive, right? Which means that the union of them is the whole sample space. And we learn what's partition, okay? And I add this graph to the slides just to let you know graphically what partition is, right? Just like this is the sample space at the square, you cut into multiple small pieces, right? They don't overlap with each other, each partition, right? And they join the union of them is the sample space. Okay, so that would be the idea of union, the partition. And now we can define probability through 3 axioms. Okay, we only need 3 axioms for it to be true. Okay, so that's how we define probability. Okay, you can see that from this definition, we don't say about anything about Raman frequency. There's no random experiment, nothing. Okay, just basically we're given some outcomes or some to be technically given some element in the set, right? Probability is just a mapping from the set to number, right? So basically, just like as I said here, right, it's an event to number, right? Or outcome for every possible event, right? You map to the numbers, all right? So if you know enough math, then it's basically the sigma algebra idea. But anyway, we are not going to do math, but just basically just from all event to numbers. So the first requirement we said for event, you want to put number there, you want to put a number always between 0 to 1. That is the first thing. I guess nothing is deep here, right? Just like because a fraction, right? It's the same idea of the Raman frequency, so it's always between 0 to 1. Okay, and you may ask, okay, what happens if I want more than 1, but you just normalize the biggest number is 1, so everything's between 0 to 1, right? And the second axiom, right, which is I think is non-empty, is although it's very trivial, you say the sample space is 1. Okay, so that means that we don't have any surprise in terms of outcome, right? It is something may comes our way unlikely, but we will not be surprised that it happened. Okay, I mean it may become as a surprise that this outcome happened rather than the other one, but it shouldn't surprise you that it's a possible outcome that actually arise. Okay, so that is the idea of that. There's an empirical part of that part, or we have an accurate description of the world that we are living in, right? There's some no surprise in terms of outcome. Okay, the third one, this is the most important assumption that would basically drives everything in the probability, right? The first 2 are basically very minor. This one is the most important assumption that allows us to define probability. Is the following. Actually, it's called additivity. The idea is that if I have a event that is a collection or a group of mutually exclusive outcome, okay? Mutually exclusive means that the interset is empty, or if O1 happen, okay? Outcome 1 happen, it can't be the case O2 up to ON can happen, okay? Only one of the one will happen, okay? But it is possible none of them will happen, right? But if one of them is true, other must be false, okay? Just to remind you again, it's possible that none of them happen. But one thing you have to know is one of them happened, the other will not, okay? Okay. And the idea under this case is probability of that event, okay, will be just the summation of all probability. So that's why the name called additivity, just adding all outcome. Okay. In the other word, right, this is actually the idea of partition. Okay. If an event, right, is being partitioned, right, by different parts, right, the probability of that big event will be sum of all small events, right? Just adding up, okay? Basically just saying that probability of this thing, okay, probability, I can cut it up and calculate parts by part, okay? I can do parts by part, have the probability of each and add together, so the same thing, okay? So not be smaller, not be bigger. So the equality is very important, okay? It's not bigger or not smaller. And there's a key thing about this, okay? And as I said last time, as technical note, okay, this looks trivial when n is finite. Okay, when we have a finite number of cutting. But if n is infinite, that would be the main thing actually in this assumption, right? And this model. And indeed, this probability definition by axiom is invented in 1930s, so only 90s ago, okay, by Russian statistician Kolmogorov. So basically, this is the definition, right? If you know probability, actually, the frequency list, the classical definition, has been invented in 1700. So it's like 300 years ago. And they would rely on the real world to define probability, right? But now we have an idea that we distinct ourselves from the real world. Okay, we don't rely on that, just a bunch of events, and we have a function on that. And of course, you probably would ask, is this going to be a valid thing? And then indeed, it's a valid thing. Okay, so is there some valid justification why this thing would be a well-defined? Okay. So this is example, I think we mentioned last time, is how we define a sample space of 6. And then if we are able to say each outcome is equally likely, then we can actually define everything in this model, which is exactly what you expect when you talk about a long-run frequency, right? But in this model, we didn't rely on long-term frequency, right? There's nothing about relative ratio there. We just define the sample space is 1. Every outcome is equally likely, then we can define everything we have in the classical idea. Okay, so that is the big thing about the probability. Okay, and as I said, this is well, it's important to expand it to infinite outcome. Okay, but for our purpose, I think we can just know it without going into the detail of why it's important. Okay. Knowing it, how is it important? I think you only learn it when you go to Department of Math, they learn it, or Department of Statistics, the advanced class, they learn. You only understand what is going on when you learn advanced calculus, not the basic integration, but a more important, another type of integration. Then you will know why important it is. But for the moment, we're just okay to know. Taking to infinity is important, just very technical, but I just let you know there's a lot of details go on if you really want to know more. And the next is by the 3 axioms, we have many rules we can derive, okay, that can simplify our computation. Okay, the first one, the complement rule, and as I said in the last class, this rule would be very useful, and we will be using it throughout our class. Okay, later you will see we will be using this all the time. Okay, so I think I mentioned it last time, but I just put it formally, right? A and A complement are mutually exclusive and exhaustive, right? Because A happen, AC can't happen, right? And they are exhaustive because the union of them is the sample space. Right, so by axiom 3, sample space will be just the sum of 2 parts, right? Because they are partition, right? Mutually exclusive, exhaustive. And by axiom 1, oh sorry, it should be axiom 2. Axiom 2 here. Axiom 2 here. It will be equal to 1. Okay, and because of this equal to 1, then you just move it the other way around, then you have this, right? So that is the idea of complement rule, right? Because adding up the 2 is equal to 1. Okay, so that is the rule there. And we also mentioned how you calculate, use this, right? We want to calculate probability of the face value less than 6, right? You can calculate what's the value of 6, which is 1/6, and 1 minus 1/6 is 5/6. Okay, 5/6 is the way we do it. Okay, 5/6 is probability because 1 minus. Of course, you can directly calculate, right? What is the value below 6? 1, 2, 3, 4, 5. So 5/6 is also fine. Okay. Basically just one object here, so that's why you can calculate everything inside only have 5. Okay, and it's easy to see that if it applies to partition, right? Because it only apply here. I just talk about A and A complement, right? And this is a partition of the sample space, right? Because you just cut it into half, cut it into random fraction. One is A, one is A's complement, but you can consider this is a divided into n different parts, right? Then probably the sample space is sum of all parts to be equal to 1. Okay, so just to remind you the partition idea, right? This, right? So adding up probability of this part and add this part, adding everything in between and the end, so equal to 1. Okay, so don't be a surprising to you that this thing would hold. Okay, and the example we have is like this, right? Just like I think more or less we stop at this example, and is we roll a die for 2 times, and what probability is the sum of the 2 results are less than 11, right? Less than 11, actually the complement will be 11 and 12, right? So just calculate number of outcome in 11 and 12, right? And then you do the complement idea, the 1 minus, and then you get the answer. Okay, so that is the way to do. Okay, I think last time we stopped at this rule. We call addition rule. Okay, the idea of this rule is easily illustrated by the idea of looking at the graph. Okay, so we look at the graph. Okay, so look at this union of A will be A plus B minus intercept B. Okay, we can see this from this diagram, right? If you try to look at this area A union B, which is this area, okay, then you can see just the red area plus the blue A circle plus the purple circle, so red circle plus the purple circle, minus the pink one, right? Because the overlap, you double count the pink once, okay, you count it twice. So take it out. So that's why it's the idea. Okay, let me repeat maybe I just draw it quickly. Maybe I draw it quickly in this here, and just to make sure that is what's going on here is clear. So you have the A is a circle, okay, and you have B, which is this guy. Oh, a purple, okay, and you have a intercept B, which is like a, I don't know, moon, whatever shape. Okay, so and what we want is this guy, A union B, okay, which is something like this shape, a heart shape. Okay, so that means that you would be talking about the formula we're talking about is the red one, okay, plus the purple one minus the overlapped area should be equal to this guy. Okay, so that is the formula. We call the addition rule. Okay, this is convenient because you can swap between intercept and union. Okay, and sometimes it's convenient to consider one way or the other, and later you will see the intercept intersection is very important thing we want to calculate, and very often you will see we will relate it to what we call conditional probability. That would be something we would be often using. Okay, but this is just graphically illustrate. I think we just stopped here last time. So let's quickly go back to the example again. Let's do it carefully because I think last time a little bit rushed. So we have a die roll once, and we're asking ourselves what's probably having an even number or a number greater than 3. Okay, So immediately you know there's a asking and or means you're asking a union. So if you call it A and B, we're asking what's A union B. Okay, so that is the idea behind this question. And A is an even number, means 2, 4, and 6. B is greater than 3, is 4, 5, and 6. Okay, and you can actually do the union thing, right? A union B is actually, you can actually calculate as you pick up everything, right? It's 2, 4, 5, and 6 because you just pick up everything there. Duplication has no point in this thing, just take it out, right? And end up you have is just 4 element, right? And this 4 element is equally likely, right? So each element have probability of 1/6, right? So we have 4 elements, so it's 4 over 6, right? So that's end up you have 2/3. So that's how you get 2/3 here, right? And you can easily see it's easy to do. But here we want to illustrate the idea of the addition rule. So you can calculate the probability of A, okay, which comes from, we have a fair die, right? So we have 3 outcome in A. So the probability of A is just 3 over 6, okay? And B only also a 3 outcome, so it's 3 over 6, okay? And since we want to do the addition rule, right? So we need to find the intercept, okay? The intercept just like find a common element with A and B, okay? 4 and 6 appear in the both, so you have 2 elements, okay? So that's why you have 2 over 6, okay? And you may ask why I do this, right? And you can see if A and B are very complicated. Finding a union can be difficult, and sometimes finding the intersection can be easy, okay? So in that case, this rule will be useful. So we just add up A and B, right? Just here, A and B is here. You subtract this guy, okay? Right, 3 plus 3 is 6, 6 minus 2 is 4. So 2/3 the same thing, okay? So that is the illustration of how this is being done. Of course, as I said, if the question is simple, you can easily find the union, right? But in the case it's not, then it's not easy to find, then you will have to rely on this rule, okay? Is that okay for this one? I think we pretty much stop here. Last class. I hope after the week and after some review, I think it's okay. And I think it's important to have a solid grasp in terms of theoretical framework. What's probability is important. Okay. So now let's have this look at this one, and this is a very commonly happen in your data. Okay, which we learned in the first class is called contingency table. This is usually the thing that you figure out from your data, right? Look at the data here. Is we have active student, okay, and there are 2 ways to classify them, right? Either they are male or female, or they pass the exam or not. Okay, here as we explained the first class, this means there are 15 males who passed the exam. Okay, so that means that if you call male and intercept, pass is 15, male and pass, right? So now the question is, if I randomly draw a student, okay, I want to know the question is whether it's a male or pass exam, okay? So what the question asks is, we have a union, okay? I want to know the union, okay? The data I have is all the intersection, okay? Because the data you have is almost always like this form, right? So that means that the data you have is almost all the time is intersect, okay? The question is asking a union, okay? And or is something like sometime you want to ask, right? And this question, so first we want to calculate the probability of male, okay? Which is just how many male you have is 40, okay? So half of them is actually a male, so it's right 40 over 80. And the second question is how likely they pass, and coming from this number, right? 35 over 80 is 0.4375, okay? And as I said, this number, the red number, the entry, right, is exactly the intercept, right? And you get this 0.1875. Now we come to the idea of doing the ORA. Okay, ORA will be just doing the probability male plus the pass minus the intercept. Okay, so we get the answer. Okay, so that is the way you calculate this number. Okay, and of course, if you don't want to do this, right, you can actually see this from this diagram. It's like here. I want male or pass, right? So basically, it's this three guy, the pink one. Okay, the pink one, right, is either male or pass, right? So we have 60 people who actually pass or male. So 60 over 80 is also 0.75. Okay, so this is the two way to do it, right? But I would think this is much convenient. Okay, because usually this is the way that why addition rule is being invented, right? So that is more convenient sometimes. Is that clear? I hope that it will make sense, but later you will see why this makes sense more when you know better. Is that a question? Is that a question? If not, then we go to the next slide, okay? Which we will be using it very often again as well, is if we have two events, okay, A and B, okay, this is a little bit tricky, is A can be decomposed in two parts, is A intercept B and A intercept B complement, okay? And you may ask why we want to do that, okay? So this is kind of what we call divide and conquer strategy. Look at A can be very complicated, okay? Later you will see the reason. And if you divide in two parts, that makes things easy, okay? And the first thing probably you want to know why we do that, right? Why this is correct, okay? Why this is correct. So look at this diagram, you will easily understand why this is correct, okay? So this A is here, the red one, the blue circle is the B, right? And this little reddish area is A intercept B complement, okay? And the plain area is A intercept B, right? So the two add up is exactly the circle, okay? So the two part is exactly at the circle. And immediately I will explain why this is important, okay? But this looks trivial, right? Because it's just like the part with B, the part without B. Okay, just repeat the statement. Okay, probability A, right, is probability A with B and A without B. Okay, so A with B, but that is the idea. Okay. Now, the proof is rather simple. Rely on A is the union of these two events. Okay, and they are mutually exclusive and partition, so that's why I add up together. It's by axiom 3. But anyway, I'm not going to. The proof is basically just the diagram idea. Okay, but since we are not interested in proof, I mean, this is complete proof already. But if you know it, it's fine. Okay, I already explained it. I already said it, right? Because this equal to this, and they are mutually exclusive. So that's why by the rule they add up together, axiom 3, because this the same, just add up different part or axiom 3 set. Okay. So the idea of this is can generalize into the following, right? If you have n event that partition the sample space, then B will be adding up for each part with B. Okay, so that is the main result we have. And I do example here. Later you see why we have to do this. I'm sorry, I should have an example here, but anyway, later you see why we do that very soon. Okay. An example behind, we'll know why. Okay. So before we talk about important thing, what we call conditional probability, let's talk about things that which is useful application. Okay. So here is what we call odd ratio. Okay. Odd ratio is something that often mentioned in the world. Okay. When you go to casino, okay, or gambling industry, or some prediction market. Okay. So let's define this way. Okay. I think this is what we call the American odd ratio. I think the British odd ratio can define differently. So I think we follow the textbook, define the American style. So odd ratio in favor of event A, we just A over A complement. Okay. And against A will be A complement of A. Okay. So if we didn't mention about just odd ratio, we default mean this one. Okay. So usually when we talk about odd ratio, this is the one we mentioned. Okay. It's in favor of event A. So odd ratio for A means odd ratio for in favor of A. Okay. Unless we explicitly write against A, so that would implicitly mean this guy. Okay. This is the thing we imply. Okay. So probably you want to know why we care about this number. Okay. So let's talk about the usage of those. Okay. So this is usually a term they use in the industry. Okay. The gambling industry. And when we are betting, we talk about odds of 4 to 1. Okay. Which means that if you put $1 on the table, okay, try to bet something will happen. Okay. If you lose, then you lose your $1. But if you win, you get your $1. You get $4 back. Okay. That is what I mean by 4 to 1. So so put in $1, you get $4 if you get it right. Okay. So what will be called fair bet? Okay. Fair bet will be, in this case, is you don't really care if you are the one who bet or you accept the bet. Okay, you don't really bother if you are the casino guy or you are the gambler. Okay, and in that particular case, in this case, two outcome case, right? So if it's a fair bet, it should mean that 20% of the time that event happened, for 80% will not. Okay. So let's see in this case. Okay. So let's see this answer. Okay. So let's see roll a die. Okay. What is the odd ratio if you get number 6? Okay. So getting 6 is 1/6, right? So this is 1/6, right? And this 1 minus is 1/5/6. So this odd ratio is 1 to 5. Okay, or 1/5. So what is a fair bet? Means that if I bet $1, I need to win $5. If not, then it's not fair. Okay. So let me repeat the statement. Okay. The odd ratio means that if the reverse of the odd ratio or the against the event should be the odd that you see in the casino TV, right? Casino monitor. It should be you bet $1, okay, for having a 6, okay, you should get $5. That is fair. Okay, is that clear? What's going on here? Okay, that would be the fair bet. It means that if I keep doing this, right? Right, means that 1/6 of time I would get $5, and 5/6 of the time I would get nothing. I will lose $1, right? And in that case, in the long run, I'll break even. Okay, although I don't talk about expectation in this, and if you go to the next topic, you will see you can calculate the expected value of this bet. You have a 0 expectation. Okay, you will see when you actually go to the next class. Sorry, next topic, you will understand what's going on. Maybe next week you understand you calculate expectation for this is 0. But just to let you know, we don't go to the detail of this. It's just saying that you be fair bet if 5-1. Okay, so you can imagine the simplest case is I toss a coin. Okay, what is the odd ratio? Coin only have head or tail, right? And the odd ratio will be 1-1, right? So you should expect I bet $1, right? If I win, then I should get $2, right? I should get $2, right? Anyway, so that would be the idea behind. Any question? Okay. So there's the idea define the odd ratio. So we want the next thing you talk about is probably the key result of this rest of the chapter is we call conditional probability, because after we define that, we define a very important result, which later just preview it. We will learn the most important rule in here called Bayes theorem. Okay, so probably preview what we're doing here. Bayes rule is I guess is the single most important thing, one of in probability theory, is how you do your learning based on data. Okay, so Bayes theorem is the following. So you would have some belief, or you believe something happened in a certain way. Okay, you have some conjecture, some idea what's going on in the world. Okay, and you collect some data, and some data will update your idea what's going on there. Okay, so that's the idea. So you may see recently the government saying, okay, let's see if the data support whether they relax the quarantine policy, right? So you can see it's a Bayesian learning, right? It's one of the rational learning is called the Bayes theorem. If you learn update based on information, okay? So if you do the machine learning or artificial intelligence, mainly most of them are actually based on this theorem. Of course, there are rules other than this, but this is the one of the main method that how computer learns is you have a set of parameter, right? Set of the setup, and then you feed in data, right? Data tells them how to improve, right? Just like look at how the auto driving thing from the Tesla, right? It's like you keep training you keep feeding data to keep training, right? And that's the idea. So this is how things being trained, right? Because look at how the auto driving happened, right? Look at the image of the world and try to infer the image, the pixel of those things is actually a human or a cat or a tree or a sign, right? These are the things that keep using this kind of idea. So basically, we can say this as a probability learning, right? Learning from probability. Okay. So that's why we need to learn what we call the conditional probability. Okay. Conditional probability just means that how we can change our probability, know something is true. Okay. So something is true means we have data. Okay. When data comes in, we learn something new and then update. Okay. Actually, that's how we learn things, right? Suppose a given a coin or different die or coin, you don't know it's fair or not. Okay. Basically, easiest, give a coin. Okay. You don't know which side is more likely. Okay. And you look at the coin, seems to be fair. Okay. You would think fair, you put 1/2 for head and tail. So what you're going to do is toss it many times, right? And if end up to be equally likely, equal number of head and tail, then you would say it's 1/2 and 1/2, right? You keep learning, okay? But if you figure out that the data keep tossing it, you may get, say, 2/3 of time is head, 1/3 of time is tail. Then you would believe that is actually the coin is unfair with 2/3 likely is head and 1/3 is tail, right? That's why you call it the Bayesian learning or Bayesian analysis, right? Just keep updating. And that actually we do in the real world, right? We do experiment, and that's how science progress, right? And that's actually the conditional probability, right? We keep doing this until we are sure enough things happen in certain way, right? That is the idea. And this is important because a lot of time we don't know how things happen, right? We have received some information from the real world, we see some data that inform us how this system would work, right? And that's how you learn. Okay. And as I said, this is important when we talk about current data, artificial intelligence, machine learning, or how actually a lot of business decisions are being made, right? So business decisions, some people would have a model, right? How consumer behave or how the demand looks like, right? Then the probability will actually you learn, right? So so the thing is, once we know, right, the probability will change. Okay. So how do we update it? Okay. So basically, this idea of conditional probability is basically just we need to make sure that our axiom 1 and 2 are correct. Okay. What is axiom 1 and 2 is every probability must be between 0 and 1. The probability whole sample space must be 1. Okay. So look at this equation. Okay. This is a definition. Okay. It can be proven, but we are not going to prove it, but we just try to justify it from the idea of axiom 1 and 2. Okay. The probability A given B will be a fraction A intercept B and over B. Okay. Why is it the case? Okay. So look at the numerator. Why this is the relevant thing? Because you know B had happened. Okay. So which means that anything outside B will be irrelevant. So which means that A intercept B complement will not be anything relevant. Now repeat the statement. Okay. We know B had happened. Okay. And we know the law of total probability, right? So remember this law here. We just learned, right? A and B. Okay. Is A and B complement and A intercept B, right? Now the question is we know B had happened. Okay. So which means that actually this is irrelevant. Okay. So put it this way, if you think the following, this is sample space S, right? Originally it's very big. Okay, this is sample space. But now the sample space was shrink, right? Because B had happened. Okay. Everything outside B is irrelevant. Okay. So what we want is we want to calculate how likely we end up in this this pink area, right? Okay. And what we said only the relevant thing will be this area over the blue circle. That will be the conditional probability. Okay. So the idea is because it's string, right? Because originally the whole square is 1. Okay. Now B had happened, it means that the whole blue circle should be 1. Right? Because everything outside blue must be 0. Right? Then you just 1 have to string inside this thing. Right? So everything you just divided by this circle. That's what we get the idea there. Okay. So that is the definition. Okay. So you can see, right, the numerator is only relevant thing. You need to divide probability B because you make sure that everything is equal to 1. Okay. Why? Because if A is same as B, okay, if A has same as B, probability B given B must be 1, right? If B happen, whatever B must be 1 because the sample space is B now. Okay. And if B intercept B, it's just itself, right? It's just B. So numerator same as denominator is 1. Okay. So this formula works. Is that clear? But we are not going to prove why this is true. Actually, there's a proof exists to prove why with this formula. But I guess intuitively, I think it's fine. Okay. I don't think we need a formal proof for that, but there is a proof for that, but I'm not going to talk about those. I mean, if you want, you can check advanced textbook. The book we have is not sufficient. So let's define it. Let's see example to see how we define. You may say this is a definition, so you don't need to memorize. You don't need to understand what's going on. This is the definition. Okay, that would be easiest for you for this moment. This is the definition. That will be fine. Just the intercept over what you're conditional on. Okay. So the example we have here is let's finish this example, then with a break. Okay. So we roll a die once. Okay. The sample space is 1, 2, 3, 4, 5, 6, right? Even number is E, large number is 4, 5, 6. Okay. The intercept of the two is 4 and 6. Okay, that is nothing new. Now, the question is the following. Suppose we are told it is large. Okay. You are told that 4, 5, and 6 is true. What does that mean? It means that the sample space is no longer 1, 2, 3, 4, 5, 6. The sample space now is actually 4, 5, 6. Okay. Now the question is, one of them is true, right? The question is, what is the probability E has occurred? Okay. And the easiest way to think is the sample space is new is L, right? In that case, under this large, okay, what is relevant for even number is just 4 and 6, right? Because 2 is no longer relevant. It's going to be large number, okay? So that's why this E given L will be just 2 outcome over 3 outcome, so 2/3. Okay. This is how you can do it if you redefine the sample space and redo everything within the sample space, right? And we know the shortcut we just learned is probably E given L is a fraction, where the denominator will be the second guy here, okay? And the numerator is the intercept of the two guys, okay? And E and L, we know it's just 4 and 6. So 2/6 in the numerator. And denominator is just 3 element, so 3/6. So that's why it's 2/3 here. Okay. So that is how you would get this number, okay? E given L. Okay. After the break, we will learn more rules, and then that will be the goal of the day. So in the meantime, we have a break. We will come back at 1:30. I'll go around to see if any question. Stop this. Take it out. So I think we can go back to here, right? It's a definition, right? A given B is A intercept B over B. So that is a decimal scale to make sure that everything is belong to 0 to 1. And I think it's good to look at the example of this, right? And we want E given L. So it's just like, given L has happened, what's the value of E? So it's just 2 over 3 outcome. Okay, so that is the idea. Okay. So now, it's just a very simple application, right? You have A, we have B, with A intercept B, where's A given B, right? So just apply directly. A intercept B is this, product B is this, then you can just put the number. That's how you do the calculation. Very simple. So now I think we have last 2 rule, maybe or 3 rule, or several 3 to 4 rule. That so this rule is what we call the decomposition rule. Sometime is we have 2 events, okay, and will be A is A intercept B. Did I jump ahead? Sorry, jump ahead. Sorry, I should talk about multiplication rule. Okay, multiplication rule is nothing but just rearrange the direction of the conditional statement. Okay, A intercept B will be probably A given B times B, or B times condition A times A. Okay, so why you would want to do that? It's because sometimes when you do this conditioning, what we call this operation is called conditioning. It's easier to do the math. Okay. Actually, you will see it now. Okay. Example. Okay. You will see why this would be appropriate. Okay. So the question is the following. Okay. So we have an urn with 3 black and 3 white balls, totally 6. And I try to draw 2 balls of it. And without replacement, just draw it without putting it back. Okay. The question is, what probably is both balls are black? Okay. So this is very classical idea. Okay. Now we denote B1 is the first ball is black, B2 is the second ball is black. Okay. So what is probability that the first ball is black? Is coming because you have 6 balls at the beginning. Okay, is 3 of 6. This is one half. And what's probability that once you draw the first black, what is second black? Second is also black. If you draw the first ball is black because you didn't put it back, so what you would have is only 5 balls in the urn with 2 black and 3 white. Okay? Because you draw the first ball is black. Okay, it will be 2 black and 3 whites out of 5 balls. So it's 2 out of 5. Okay, so that's why the intercept. Okay, that's we use the multiplication rule will be 2/5 over 1/2. Okay, they times together is 1/5. Okay, why this is easier to handle? Otherwise, you have to how to do this 2 black ball. You have to list all possible scenario. Okay, first one is black and second one is black. What is probability that you have to do? First ball is black, second one is white, and white and black, and white and white. There will be many cases that will make our life difficult to calculate. So that's why we learn this rule will be much simpler. Okay, and it will prove convenient. Sometimes you will do it in a tree diagram. Okay, that usually you would draw in this way, right? You start from the beginning. Okay, from the first draw, it either is black or white. Okay, which is equally likely, right? Because you have 3/6 and 3/6 is here, so it's 1/2 likely you would equally likely end up with this outcome or this outcome, right? If you have the first one is black, then you only have white and black here. Okay. If you the question is so Ricardo, can you repeat the question? Is it same as sorry? What's the question? May intercept B is A given B, not it's A given B. It's not the same. It's not intercept. It's A given B. Okay. Anyway, so you can see is B back and right will be because only have 2 black ball, so 2/5, 3/5. Okay. And how likely end up here? Okay, right? With black 1 and black 2, right? So here actually we're doing the by drawing this, right? Actually you're doing the multiplication rule, right? You multiply this times this. Okay, you multiply backward, right? 1 by 1, right? Then actually it's called the multiplication rule. That's why you multiply. Okay, you multiply this times this, right? How you get this end up here? You multiply this times this. Okay, that is the multiplication rule. Okay, some of you may have learned this from this diagram from your high school, but that's the idea. Okay, and go on so and so forth, right? So you get all this at the end, then you will say, okay. So that's how you get this rule, and this rule will be very useful later. You see the Bayes theorem. Okay. And is that okay for this rule? Is called the multiplication rule. As you can see, it doesn't really matter which one you conditional on, so you can basically swap. Is that okay? Now, is there any question? Okay. So now we just try to combine the 2 rules, okay? The total probability rule and the multiplication rule, right? Because this is equal to this by the multiplication rule, and this part is equal to the second term. This is by the multiplication rule, okay? And some of you actually asked me in the break, right? Some of the textbook will write this equal to this as the total probability rule. Okay, some of you actually asked me, and they're the same thing, right? Because I think I follow textbook definition. That is called the, I mean, whether you call the first line total probability rule or second line doesn't really matter, the same thing, because the multiplication rule always holds. So up to you what you want to call. Okay. And of course, this can generalize to any, this, I have B and B complement, but same as you would want to extend it to any partition would hold. Okay, you can, if B is a partition, you can have B1, B2, B3, Bn, the same thing. So I think it's good to look at this example again. This is an example where you have 2 different beds. Okay. Bed number A have 4 white ball and 1 black. The other we have 1 white and 1 black. Okay. And the question would be, we are going to close an eye and choose a bed at random, and I close the eye again to draw 1 ball from that bed. Okay. So just repeat the statement. The exercise we're doing here is for 2 beds, A and B. A have more white than black, and bed B has the equal number of black and white. Okay, and we close our eyes, okay, and try to draw a ball from there. The question is, what probably is the ball is being white? Okay, and here you can see the question will be said in the way that white actually can be mean 2 things, right? White can be coming from bad A, and white can be coming from bad B. Okay, and you can only come on one bad, right? So there's mutually exclusive and exhaustive. So that's why you can divide it into this. White is A and B, right? Because A's complement is B, B complement is A. Is that clear? So that's why this apply. Okay, why this work? Repeat, because A and B are complement. Okay, and now I use the multiplication rule to divide them into this part, right? You conditional A times A, conditional B times B. Okay, and if you know the ultimate form of total probability rule, you can from here up to here, up to you what to do. Okay, and if you are in A bad, what's probably getting white? You have 4 of the white ball out of 5, so it's 4 over 5. And how likely you get a bad A is 1/2. Okay. And if you end up in a bad B, how likely you get a white is 1/2, because 2 balls you choose 1/2. And how likely you get black is also 1/2. Okay. So end up will be 0.65. Okay. So you can see if this is the divide and conquer idea, right? Asking you the white, you divide white into bad A and bad B. Okay, so that makes calculation easier. Is that clear? Okay, so actually this is something that often used. Later you will see. It's often used in finance as well. Okay, maybe bad A is a good news, bad B is a bad news, right? If good news is more likely the stock goes up than go down. If bad news is go down more than go up, right? And then you look at the stock price actually move up, okay? Then you try to infer whether it's a good news or bad news. Okay, so that would be later idea we talk about Bayes rule, but this is the concept we were going to learn. Okay. Now you can see this from this slide. I just added to the I just added, but without it I think it's fine. So bad A or bad B, okay. Either you can go up or go down with equally likely, because I am up with A or B, right? And if A, I should change to black to green. Sorry, I should have changed back to green. Green. The reason why I want to change to green, because black and the B are very similar. So I change to white and green. And I will have white, right? Will be 4 over 5. Green will be 1 over 5, right? So A and the white will be just, you go back to multiply. And A and the green will be just multiply backward, right? From all the way to the root, right? To the bench all the way to the root. And similar to the branch below, that you can do all the same calculation, right? So the question being asked is, what is the probability of white? So basically just you add up this and this. Okay, I stop here to see if you have any question. So because this is a little bit more complicated. Because white is either A's white or B's white. Okay, is that clear? So drawing this will be very helpful when you try to do your assignment. Okay, try to draw this and try to fill up the diagram. Then will make your calculation more clean, more clear what's going on. Okay, but if you are, especially you're a graphical person, you learn by picture, that will be easy. Is that clear? Sorry, I changed to green because if I use B, then you will get confused. So that's why I changed it a little bit. Is that okay? Any question? Just no more question? Okay. If that's okay, then we'll define this definition of independence, and then we'll go to the most important part, base rule. Okay. Independence is a very simple idea. Okay. You can define 3 different ways. Okay. They're equivalent, so you just need to check one of those. We're done. Okay. The idea is very simple. Probability A given B happen is same as A, then A and B independent. Why? Because whether B happen or not has no impact on A. Let me repeat the statement. This first one is saying, I tell you B happen. Okay. How likely A happen? I mean, telling you B has no impact on that. Okay. So that's the same idea. Same, you go for the second line. Telling you whether A happen or not actually has no impact. Okay. And the next one is very little bit trickier. Is the intercept. It just multiply together. Okay. Just multiply is fine. Remember the rule of multiplication rule said the following, right? It's either A given B times B or B given A times A. Okay. And if you have either the first row or second row, then you go to here. Right? So exactly what's going on. Let me repeat the statement here. Okay. This equal to this is we just learned. This is the multiplication rule. Right? These two. Okay. And if either the first line or second line is true, this will return to here. Right? Because this will be same as this guy, right? And this guy same as this guy. So regardless of which line you look at, the same thing. Okay. So is that okay? Is that fine? So that is we say they're independent. Okay. So that is a very important idea to say what is independent. We need to require this. Okay. The probability that 2 events are independent. Okay. So what application of this, right? So very often these days, right? Our expert from the government said, okay, taking the vaccine and the people who die has no relationship. Okay. So how to prove this? You have to prove those people who die, the proportion will be the probability who die, right, to the vaccine, the same, then you're done, right? Or you can prove it, the death, probability of dying, taking the vaccine, same as the probability of dying, regardless of the vaccine. So the death rate is not increased, then they're independent, right? So that is something we often use, okay, to prove they are no different. Okay. Very simple idea, which you will see in your second assignment, but we'll be saying the following. I have the A and B and A intersect B, asking they are independent or not. Okay. The simplest thing is just to multiply them, which is not same as the intercept, then you're done. Okay. It's very simple. Okay. The check is whether they're exactly the same. If not, then no. Okay. So very, very simple. Now we at the end, we want to go to this one. Before the end, we just try to say independence and mutually exclusive are completely opposite. Okay. Mutually exclusive means the following, right? They can't happen at the same time, right? So the intercept is 0. Okay. And using the addition rule, okay, the union will be this plus this minus the union, which is 0. So that's right. The union just sum of them. Okay. And independence means the intercept is the multiplication, right? Because this is definition, right? The union will be same as before. Okay. And okay. And that means that if the two events are independent, okay, they cannot be mutually exclusive, right? Because mutually exclusive means what? A happen, B cannot, right? But independent said A whether happen or not cannot tell you B, right? Or B happen or not can tell you anything about A, right? So when you have independence, you cannot have mutually exclusive. When you have mutually exclusive, you cannot be independent. Okay, so that's why there's two events are mutually exclusive. Okay? And that's very important, right? Because we don't want to mingle this idea. They are different. Okay, but it's technical, so just for you to have fun. So finally, we want to talk about this final rule. Probably this is what we talk about today. It's a very important rule, and that's the rule that underlie a lot of medical tests. Okay. The main of this rule is the following. We have B given A. We want to swap A given B. Okay, so that is the idea. What we want is we want to swap between A and B. We need to rely on the Bayes theorem. And very soon from the example, you will see why swapping this is the main thing we want to do. Okay, the main thing is learning. Okay, is once you have data, we want to learn from that. Okay, very soon we will see the example, you will see why we do that. But let's see the formula here. This A given B, okay, the denominator is B, is not surprising because there's definition of conditional probability, right? And the numerator, okay, and just quickly, this guy is just A and B, right? This is coming from the this coming from the multiplication rule, right? And you can decompose in this way, right? This equal to this thing is just a definition of conditional probability, right? There's nothing new there. Okay, I think this rule I think is invented in 1920s by Bayes. Okay, but nothing new here, right? It's very simple, right? The proof is very simple. As I said, this definition, right? Conditional probability and multiplication with this. You just put this on the bottom, but on the top, this is the rule. Okay, I mean, you think there's nothing new here, right? Nothing deep here, right? It's very trivial, right? But it has a lot of application. We will show you the application. Okay. So let's see this. I mean, I think the graph is not very important for this moment. Let's look at this example. Okay. This question is like the following. So this is a very common thing you would for actually fit very well when we are COVID. So now consider a case we have 40% of population infected. I think it's roughly the same for the COVID. I guess most of the population actually this is true. And now we have a imperfect medical test, okay, which does the following. If you are infected, you will get the result, positive result is 0.8, okay? And the next one is you are uninfected, you will still get positive result 0.4. So the test is not very accurate. Okay. Okay. If the test is perfectly accurate, then it's done, right? Once you've done the test, you are fine. So the question is, if a person is infected, okay, we want to know this probability because we only can able to give a test, right? So let me repeat the question here is, this is the knowledge we learn from a lot of experiment. This is our knowledge, okay? Now what we have is of a data of a guy with positive result. We try to infer how likely that guy has a disease, okay? That's very important, right? Because a lot of tests is not perfect. And we want to know, given this new information, how likely a disease, right? And although we don't cover in this one, you can imagine that what is the probability that if I give him 2 independent tests, okay, if it's still positive, how likely he has disease, right? So then you can decide how many tests you needed to make sure that he has no disease or disease, right? So that explains the reason why sometimes you need to do the RAT, you do the PCR, 100 PCR, you have to be done in order to make sure that that guy has a disease, right? So here's a question, okay? Now let's try to see. I just do one test, okay? Make sure that is simple enough, okay? So let event A is being infected, B is positive result, okay? So from this question, what do we get is infected has 40%, okay? Given has infected, okay? And you have positive test result 0.8. If you're not infected, the positive result is 0.4. So you want to know the following. Given a positive result, what is probably being infected? Okay, so that is the main question. Okay, so that is the main use of the Bayes rule, right? You have some prior knowledge. Okay, you have some prior knowledge. You know, you can imagine how the mechanism of the test work. You want to update this given you have the result. Okay, is that clear? Is that clear what we are doing? So because this is very important, and this is how you learn, right? You keep this is new information. You can imagine this new information. Okay. Look at the original information is here. This is the original info. You start with, if you pick a random guy, okay? If you don't do any test, okay? You don't do any test. A random guy has a disease is 40%, right? You just do any test, okay? So now you put a test on that guy, okay? That guy has positive test result, okay? The question asks, how likely is getting infected, okay? Instead of putting 40%, okay, 0.4, you have a new thing here. What do you learn from that? So from 0.4, okay, you can imagine without doing any calculation, it must be bigger than 0.4, right? Because he got the positive result, right? If you got a negative result, you'll be below 0.4. So that's how we learn. Of course, you can keep testing it, that guy, then you would keep doing that, okay? So let me repeat, if you happen to do the test again, right? You just replace what we have here in here, and we do all the optimize, we do all the calculation, okay? Because 0.4 is our initial input, okay? If you do a test on him, he still have positive result, then you will do this calculation. And you keep doing until this number you think is good, then you stop doing things, right? Is that clear what we're doing? So the original input is 0.4, which 40% is infected. And then you just do the test and see if you can learn more, okay? Now, first, how can we do that? Okay. The Bayes rule is like the following. what you have is we have this guy A, right, which is 0.4. This is the black one. I don't know what color, red. Okay. This guy, we know it is 0.4 because this is what we start with. Okay. And we also know this guy. Okay. If has disease, 0.8 will be likely. Okay. So what is left for us to calculate based on the base rule is the denominator. Okay. What is the probability that one has a positive result? Okay. So how can we do about that? Okay. This, the denominator, okay, what we're using is we call the total probability rule, right? We divide in two parts, A and B, A complement and B. Okay. And we will do the multiplication rule, divide them into two parts, right? B given A times A, B given A complement times A complement. Okay. And this number we know, this number we know already, and this number we know already. Only this, the last number didn't know. A complement. Okay. But A complement using complement rule, like above, it just 1 minus A itself is 0.6. Okay. So you just plug in all the number here, you get 0.656. Then what we get at the end is 57.14. That will be, we learn it because before we believe a random guy is 0.4. Okay. Now we have 0.5714, more likely. Okay. And the next question probably you will want to ask, as I said, is you will still think I need one more test, right? Or several more. Okay. You may set a threshold when you want to stop. Okay. But what you're going to do is you put this number here, right? If you're thinking that I do one more test, he's still positive, what will you get? That would be the way you do it. Okay. But that would be beyond what we. Is that okay? Okay. So you keep doing this, keep updating until this number would be fine. Is that clear what we're doing? Okay. So let's see the diagram, then you will see what we are thinking in our mind. Okay. So the guy we start is either the population is either the affected or unaffected, right? We have 0.4 here, right? Actually 0.6 is here because it's either infected or not, right? And if you're infected, okay, you get a positive result, it's 0.8. You don't get a positive result, which is 0.2, right? And if you are negative, you're not infected, you still get positive result 0.4, you don't get 0.6. Okay. So that is, this question gives you the model. Okay. The question is actually asking is, given you're here, okay, right? You want to know this here, given it is here. Okay. You want to know the probability of positive, right? You're infected given positive result. Okay. So basically what you have is sum of the red, okay, because you get positive result, okay, over the top branches is the probability. Okay, so that is how what you're doing here. Okay. So where lastly, just one second is here I have either you got a disease or you got a positive result or not, but you can decompose it, the A, into many outcomes. This would work. Okay. So when you check the textbook or the thing, they call this is the base rule, but that's no different from what we learned. Okay. So So let me stop here. I will see you on Thursday.